This is section 9.5. Section 9.5 deals with the reduction of alkynes. And we've already seen one type of alkyne reduction that we covered in the catalytic hydrogenation section, which is the cis reduction or syn reduction of alkynes using hydrogen and Lindlar's catalyst to make a cis alkene. However, because as chemists, we like to have all possible tools available to us, we want to be able to make not only cis alkenes from alkynes, but also trans alkenes from alkynes as well. So, to make trans alkynes, what you can use is sodium metal and liquid ammonia. If you submit some alkyne, like this internal alkyne here, to sodium metal in liquid ammonia, you get the trans reduction product in good yield. And the mechanism for this reaction is fairly simple. Sodium metal is a very strong single electron reductant, and that means it will give the electron to whatever the lowest energy molecule is as long as it can. So a single electron is given from the sodium metal. Notice the single barbed arrow here. Because this carbon would then have too many valence electrons, one of the pi bonds splits heterolytically, meaning that one electron goes to one carbon and one electron goes to the other. When this happens, it forms this vinyl anion radical, which then can deprotonate the ammonia that we have from the solvent, liquid ammonia. When it does deprotonate that, you end up getting this type of vinyl radical. Once you form the vinyl radical, a second sodium metal can then give an electron to make the full anion, and that anion can then deprotonate the liquid ammonia just like it did before to give us our trans alkene product, as you see here. And the question you may have is, why does this happen selectively in the trans stereoisomer? And the answer is because if you have the cis isomer of the anion radical, in that case, you would have both the anion electron cloud and the radical electron cloud on the same face of the alkene. And there would be a lot of electron repulsion here. This would not be a very happy molecule. So to alleviate that strain, that electron-electron repulsion, you have an isomerization. It flips to give the trans isomer of the molecule, and this is actually stable. It's stable enough to do the reaction, and as soon as you deprotonate ammonia with this anion cloud here, then you've kind of locked this, this conformation in place. So just to make things more clear, if you have an alkyne and you treat it with H2 and Lindlar's catalyst, you can stop at the cis alkene. To get the trans alkene, you need to use sodium metal and liquid ammonia to get the trans alkene from an alkyne. And this was section 9.5.